Howdy folks, today we are going to go over search algorithms. This is mostly how to find things. These can be really important, not necessarily always by themselves, just as a search algorithm, but they are often very important as part of larger algorithms. There's a lot of cases where we have the need to find data within a set of data or list of data very, very quickly. And this is kind of going to teach us how. So, there are three kinds of algorithms of search algorithms that we're going to go over. Some of them have different requirements, some of them have different runtimes, some of them are a little more complex or less complex to implement. Starting off, linear search. Linear search is very simple and basically involves looping over a list. You have an array of data and you're going to loop over that array of data one by one until you find an element matching your search term. Its time complexity is O of n. Because, remember, time complexity is worst case. And in the worst case, the element that we're looking for is at the very end of our list. Yeah, sorry, I keep forgetting my hands are backwards here. Very end of our list. And so, it has that time complexity of O of n because the very worst case is that we have to search through the entire array to find it. The space complexity is kind of interesting. For most space complexity, we don't count the original list of data. We count any new data that we need to create. So in this case, looping over a list, we don't need to create any additional variables to do that. So its space complexity is O of 1. It's constant. This is one of the slowest search algorithms, but also the simplest because it's just looping. So let's take a look at how that would work. Let's say we have this data, right? This is an array of data. We're looking for the number 12, which is here. First thing we do, we start off looking at the first element, which is 5. We say, is 5 12? It's not. We move on. We've looked at 5. 4, is 4 12? Nope. What about 3? Nope. 8, 88, 324. And then finally we get to 12. And we say, oh, we found it. We're good. This can be used for a number of things. This is not just numbers necessarily. It's just numbers are convenient. This could be a list of objects that you're checking some specific key on those objects to see if it matches some criteria. That could also be a thing to see, do I have any users whose age is 12, for instance? And this might have a bunch of other data attached to it. So that's linear search. Very simple. You just loop through the list. Very slow. Next is binary search. Binary search involves treating the list of data like a binary tree, and we're going to kind of see how that works in a minute. Treating lists like binary trees is not super difficult to do if they are ordered. Binary trees are actually a specific data structure, and if you're inserting and removing from the binary tree, you want to have that actual data structure just because it makes it's a little easier to work with. But if you're just dealing with a list of data, you can treat it like a tree. This only works on sorted data because of the way that binary trees are set up, and again, we'll see why in the example, but unsorted data, this will not work at all. These two criteria allow us to eliminate half the data left with every step, which gives us a time complexity of O log of n, which O of n and O of n squared, as n gets really big, they get big. Log n kind of has a graph more like this. It's very, it doesn't grow very quickly, basically, especially compared to the amount of data you're feeding into it. This also has a space complexity of O of 1 because we can work on the existing array and we don't have to transform it at all, other than sorting it, which sorting can happen in place. So there's an example. And you can see I've sorted our data, 1, 3, 4, 5, 8, 10, 12, 88, 324. And also I've given you the binary tree representation on the right. Is this a great drawing of a binary tree? It is not. I am not that skilled in Google Slides. But this is, you can see now, right? This data, every single number in here is in here. We're just representing them a certain way. How can we do this? Well, the root, 8, is going to be the middle of the array. We know the middle of a binary tree is always going to be the midpoint, the average of a sorted list or of the sorted data set. That's why it's important that this be sorted. 8 here is that midpoint. If we look, we say, okay, what's the midpoint of here? We take these 4 data points here, and since it's, I just decided arbitrarily, because it's even, we just jump one up, right? So we go to the 4. then we look to the left and the right, and etc. Same here, we go here, it's 88. So that's how I built this tree. And using that algorithm, you can treat this as a binary tree without actually transforming it into a binary tree. Okay? So, first node we look at is 8, right in the middle. We can get that very easily in constant time by dividing the length of the array by 2 and rounding it, taking the ceiling of it. Okay, and that gives us, out of 9, that gives us 5. 8, that's our midpoint. Okay, so then the next thing we say, okay, is 12 greater than or less than 8? If it's less than, we know it has to be in the lower half because, again, this is a sorted array. That's really important. It has to be. We can assume that if our number is less than 8, it's in these 4 numbers. Greater than 8, it's in these 4 numbers. So we say, okay, what is greater? What's our next midpoint? We then kind of recurse into this array, this subarray of 4. We say, okay, half of that rounded up. Well, technically that's 2, right? So 4 divided by 2. This is the 2th. Whoops. 88 is the 2th element, which is in index 2, which is actually the 3rd one. So we go there. We say, okay, we're now at 88. Now we've jumped here. So you can see we've already eliminated half the array. We know it cannot possibly be any of these values. So we're not even going to bother to search them. Next thing we say, okay, is 12 greater than or equal to 88, or greater than or less than 88? Because we need to do that check again. Is it on the left or the right? Okay, well 12 is less than 88, so we go to the left, do the same thing. 2 divided by 2 is 1, so we look at the 1th index, which is actually going to be the second one, that 12. We jump down here. Now, if we were doing the 10, if we're actually looking for 10, we do that jump again into that subarray. And you can see this was 3 steps on 9 elements. This only gets more... as you do a binary tree, because they only have 2 arms, it does get bigger, but it gets bigger in a logarithmic fashion, which means that the n complexity of this search is actually the height of that tree. You know this is a tree of height 4. The most elements we go down is 4. Okay, so if we added another level, we'd have what? 1, 2, 3, 4, 5, 6, at least 7 more elements in here, but our complexity will only go up by 1 because of the way that this tree is structured. So binary search is very powerful in this way, and it takes a little bit of wrapping your head around, but you can see that basically I haven't done anything to this list. I haven't transformed it at all. I'm just visualizing it differently. And because I'm allowed to make those assumptions, because I know it's sorted and I know I'm treating it like a tree, I can use that visualization to make assumptions in my algorithm that get me to the right number with less steps. Binary search is very common. So, hash search. This one is if you really, really need to do a lot of lookups over data. If you're doing one lookup, this actually has the same complexity as a linear search, because it involves converting the list into a hash map or a hashed object. What that gives us is hash maps have a constant lookup time of any key. Any key. So I can put in there, here's my key that I'm searching for, and if I hash everything by that lookup, by that value I'm searching for, I know immediately in constant time if that value is in there. It does involve converting the list, which means you pay up front an O of n cost because you have to loop over your entire data set to hash all of it. However, each subsequent lookup is O of n in constant time. It's very fast. So if you know you're going to do one single lookup of your data, hash search is not what you want. You probably just want to do linear search. But if you know that you've got a data set of 10,000 items and you're going to do 300 lookups on that, it might not be that expensive then to hash search and then do all those lookups in constant time, because you're saving that time over the lifetime of how many you're searching. Like it kind of that O of n spreads out over a bunch of searches then, which means that it's a little more efficient. It has a time complexity of O of 1 because lookups are immediate. It has a space complexity of O of n though. That is because you're actually having to allocate more memory because we're creating a new variable that is going to store that hash, right? And so, yeah, it's so if you're tight on space, Hash search might not be for you, but usually that's not a problem. It can also work on unordered data. Your data does not have to be ordered. Hash search doesn't care. It's got it all at the same level. So the example here, we've got our key and value. In this case, I just chose true. So our key, remember, every single one of these keys we can look up immediately. Our value, we just get that value. So I just say, give me the value for this, for 12 in this hash, and it returns it immediately. If it has it, it returns null if it doesn't have it, which means I can check if this value exists very quickly just by checking whether its return value is null. In the case of this is a more complicated object, the value would be that object instead of being true, so that you could look up that object by key. And then one step, I tell it find true, it hashes that true. The way that works, it kind of has to go into how hash maps handle their data under the hood, but basically it can look up that 12 immediately and know whether or not it has it. You just have to pay the upfront cost of converting. So hash search is not a magic bullet, because you do have to pay the upfront cost and it takes extra space. But if you have the space and you have the time to do that one-time conversion, it can be very good later on. And that's all we got for today. There's not a lot of different ways to search something, unfortunately. The most common one you'll see if you have unordered data is linear search. If you have time, you'll hash search it. If your data is ordered, which remember, ordering something, well, we'll get into that later, but the most efficient ordering algorithm is n log n. And so that means you have to pay that ordering time ahead of time. Then your search goes into log n, which can be kind of nice. Anyway, hope this was helpful, and I'll see you all next time.